So hello and a warm welcome to our webinar. It's now time for us to kick this webinar off. The title of this webinar is a demonstration of an interlocking design automation solution. So before I hand over to today's speaker, I just want to inform you that you can ask questions whenever you want during this webinar. We will answer your questions in the end of the webinar. You use the question mark icon on the control panel to go to webinar if you want to ask questions. So please use that functionality because we really have the experts with us here today. And when you ask questions, there is no one else on the webinar that will be able to see your questions. We will be the only ones. So use that functionality and ask questions. And after the webinar, you will later on receive an email with a copy of the presentation, just so you know. So now I would like to hand over to today's speaker, Jesper Karlström. So,
thank you, Lars. Yes, I'm Jesper Karlström. I'm in charge of engineering at Prover, meaning products and services. I've been with Prover since 2008. Started as an engineer and now managing this department. I will show you today how we our Prover Trident process. So it's a full tool suite for development and V&V of signaling interlocking systems. There will be some recommendations in the end of this demonstration if you want to develop things in this way yourself. And also, as Lars mentioned, a questions and answer session. I think it will be about 30 minutes from now. So feel free to post questions in the text box with this. This demonstration today will be around some mock-up signaling principles that we invented only for demonstration purposes. I will not go into deep discussions about these signaling principles, and it's also important that you don't think too much about them, but more about the tools and the process, because the tools I'm about to present can be adapted to any signaling principles. We just have to choose something in order to have something to demonstrate. So I will quickly go through the 5 different signaling aspects we do have in this system, simply so you can follow the examples I will give. Red is stop, not very surprising perhaps. Then we chose to do consistently like this. The upper light in the aspect is the main light and the lower light is the distance signaling. So if the upper light says green, it means you can proceed with unrestricted speed. If it says red, it means you should not proceed at all. And if it's yellow, it means you can proceed, but with restricted speed because there is a reverse switch ahead in the route. Then the second light, the lower one, simply gives the driver of the train information about the aspect of the next signal. So if the lower light is red here, it means that the next signal will be at stop. If the lower light is at green, it means the next signal will be at unrestricted speed, and so on. Okay. The contents of this demo will be first, we look into the specific application process. That is how to configure a station with these mock-up signaling principles. How to use simulation, both interactive simulation and scripted simulation, how to do formal verification, and how to do code generation. Then, after having done a specific application, you normally need to certify it to see that it complies with Senelec norms or similar. And as part of this certification is to prove safety. So you need some kind of, according to the norms, you need some standalone tool for this, so we don't mix up the design and the verification. And we provide a standalone formal verification tool called Prover Certifier that I will show you here. Finally, I will say a few words about the generic application process. It's maybe a bit upside down here because you normally start with generic application process and then you do the specific application process. But I wanted to focus on the specific application process because it's by having a really efficient specific application process that the development becomes smooth. With the generic application process, I will only show you how we can change a few signaling principles and investigating the impact of those changes using simulation and formal verification. Okay, that's enough for slides. I'm going over now to using the tools, because the intention with this webinar is that it should be very much hands-on. So let me start the Windows application we provide called ProRilock. When you want to start a new project, you press the new button here, and then you have to choose a name. So I will make a small siding station, and because it's entirely mock-up, I simply call it siding. Then you can provide ProRilock with the different packages of signaling principles. And here, for this purposes, we have the demonstration packages 4.0. And we also, last year, we launched a new layout editor, so I will choose the new one so you can see how it looks. Okay, and you can also, by the way, choose where to put all the files connected with this project, but I'm fine with the default here. Okay, when pressing OK, it will load now all the packages I chose, and also check all the packages for integrity and compute their checksums. So if you have some, for example, some documentation saying that certain packages have been approved or should be used, you have the chance here to verify their checksums. And also in the packages themselves, there are printed checksums, so the tool can check that the checksums are actually correct. So for example, if you change a file in the package, you will be notified because the checksum will not match anymore. Here's typically some metadata to input, like versions of this project, maybe the customer that ordered it from you, and so on. I will just leave everything blank currently. The packages here, you can see demo 4.0, the one I chose, and the other ones are packages that this one loads. So you can have packages that depend on packages that depend on packages, and so on. So it will saturate all this and load all the packages we need. Okay, let's get started. So we want here to draw a little siding station. So I take the track symbol here. We draw now like in a simple painting program. All the tracks I want. Let me do like this. And when we draw here, we get a switch. Then we want to switch here as well. Now I don't particularly like the names here, so I will just call this one 1, and I call this one 2. Okay. By double-clicking on a name, I can just change to a different one. Okay, now let's put some joints. So I take one here. Maybe I put it there. And I need to invent a name for it, so why don't I call it D1, for example. And then the second one here. D2, put one here, D3, and then we want one here, D4, put one again here, D5.
Yes, but we've got a question
Already?
About packages. Can you explain the packages a little bit more in detail, what they mean and how they're used?
Sure, I can. Okay, so the packages I show, maybe I can show them again. We didn't want to develop a tool that was tailored for one set of signaling principles. We wanted to develop a tool that could be used all over the world for all different signaling principles. At the same time, we know that infrastructure managers are reluctant to just adapt their principles to different suppliers. So we made everything entirely configurable. So when I open a new project, I choose a set of principles from a drop-down menu, and you can install packages into ProRilock, and so to expand this drop-down menu of choices. Exactly what we have in the packages, the contents of the packages, I will go through a bit later in the generic application section in the end, so bear with me. I leave you there with this question, but I'll get back to it. Okay, now I want to join here as well. That was the last one. I hope you were satisfied with the explanation. Otherwise, feel free to ask more if you have more specific things, and I will answer them in the end of this webinar. Okay, let me put some signals here. I want some entrance signal, maybe here. Would be nice, and I call it S1 because it's at joint D1. And then in the entrance here, I right-click to change direction, S6. By pressing space, I get a new one of the same type. This one should be an exit signal. So let's call it S3. And this one is also an exit signal, S4. Here is S2. This is S5. Oops. Oh, okay. I couldn't do this. I by accident wrote S4, and there was already such a signal, so I wasn't allowed. Okay, you can adjust if you like the labels here a bit, if they are too close or something. Okay, now let's put some track circuits here. So I pick one, and here let's call them T1. And here, let's call them T2. T3. T4. T5. And T6. Maybe I move this bit closer like this. Okay, if you hover over one of the names, you can see what the names are for. Like here, it will highlight the signal and where it's placed, like this. Now I want also to add a name for this, so it's a location object. It doesn't mean a lot, but at least I can put in a name. This can also be configured. So for some customers, for example, they have been using this for different controllers. So maybe they have an interlocking with 5 controllers, and then they can put all those controllers out there where they belong. Then we take a direction. Maybe I should call this bit generic name east. And then the other direction, let's call it west. Okay. Move this around a bit. Okay. So you see, I configure this station as in a painting program. Normally, there are also some other data like timer values and stuff that cannot be graphically represented in a good way, and they can be entered as tables instead, if you like. Okay, now we have everything we need for this mockup project. There are actually some other kinds of signals I can choose. I can actually change a type to a shunting signal, but here for this purpose, I choose to work with only main signals. When done, we can press this button. It starts a computation using all the generic signaling principles that are put into the packages, using also the configuration data that we just entered here by drawing on the canvas. And using these input data together, it can compute the logic for a signaling system for this station. So this is what I do by pressing this one. It computes now the design. It also computes which test cases you need to do for this interlocking, and it computes also safety requirements you need to prove by formal verification. Here's a simulated window opening. I prefer to have 2 screens, so I have this window on one screen and this one on another screen, because there is lots of useful information in the simulated window. Now I put the other window behind this screen because you can only see one. So let's look at this first. You can see here that the signals they are now all red. You can also see that the points here on the switches are actually straight. So I can try to use this. If I right click here on the signal, see a lot of commands that could be sent from the office system. So I now simulate that the office system send a command, and I can choose here. I can request the route to be locked. I can cancel the request that has been stored by the interlocking. I can release a route that has already been locked, or I do the same for the other route here. I can also look at various other stuff for, sorry, not look at, I can set parameters for the testing. GTS means generic test specification. And then I can also run a train. So let's first lock a route here. And we can also request the route to be locked here.
Yes, we have another question. Jesper, the small d's and the small t's,
yeah.
Can you explain what they stand for?
Okay, yes, sure. These are just names. So when I put here the joints, in this package you are supposed to name all the joints. That's not necessary in all signaling principles, but some infrastructure managers use named joints. So for consistency, I used D for all the joints. I think it's abbreviation for the limiter. And then I used T for the track circuit. So this is a track circuit, this is another one. I consistently named them T, but you can call them cucumber if you like. It doesn't matter at all. Okay, I simulated here now two simultaneous routes, and I can also click on tracks to actually occupy them like this. So I can click on the track or on the label of the track. So now we can simulate that the train is approaching. When I click here, the train will occupy this track, and you can see that the signal turns to red here while this is still green. I can request a new route, by the way, exit here. And let me also request an exit route here. So you can see here this requested gray route. It cannot lock because there is a conflicting route. And this is where I also have this request cancellation, so I can remove the request. But now I want the request, so I let it be there. Okay, if you look here at the occupation, we now pretend that the train reached this track. So I remove this. You can now see that this switch is moving. The flashing little arrow. The switch locked. Okay, sorry, I still have an occupancy here. If I remove that one, we can see that the exit route locks. And now it says green, expect green here. Okay, so let's take a train in at the station here. Occupying there, next occupying here. Now you can see that the switch here moves and the route locks. And now the train can continue. So we can actually here also click run train on route, and it will automatically spend 2 seconds per track and leave the station. This is a kind of what I call ad hoc testing. You can try whatever you like, or you can also use it for explorative testing and things like this. But it's also useful to know that you can use scripted tests. So, for example, here, the simulator, if you open it up, it has some predefined test cases. And again, these are not built into the tool itself. It's part of the packages. So there is a testing package that defines that for each route, you're supposed to try 3 different things. One is this. If you click on it, it explains this is to test that routes are released correctly after traversal of the train. And there are 3 different ones. This is to test that parallel non-conflicting routes are available when a given route is locked. And so on. You can open up here to see that this test is run for all the routes. And if you start here, it will run all the tests, and it doesn't run them in real time. It runs them as quickly as it can. So it simply advances time very quickly. And you can see here that everything became green. If there is an error somewhere, it will become red instead here. I will show you a bit of this in the end in the generic application demonstration. Okay, let me also do some formal verification. We have a number of requirements here, also built into the packages, things we are supposed to prove. So let's run them. You see, it was fairly quick actually. 310 requirements proved in 0.39 seconds. We use our model checker PSL inside ProRilock, and also when you develop something knowing that it will be proven correct using formal verification, then you take care during development not to take any, not to cheat or to make it, to actually follow up all the time that the safety requirements can be proven. So you fix the design rather than spending a lot of time in formal verification. That's why we think it's very important to have formal verification as a built-in tool into the development environment. Okay, now we have tested, we have formally verified, and it remains only to generate the code. So let's do that. I just press OK. In this project, we generate code, C code. This has now been generated, all these folders with different stuff. It can be C code like here, or it can be any language. In fact, the generation of, so we build in this tool a mathematical model of the system, and then the generation of code is more or less only rendering the code in the given syntax of the language. So we can do C, but we can also do many other different languages. Okay, so we have now tested, verified, and run code generation. And it's time to certify that this generated code is correct. But before, I just want to go back and say what we did. We configured a station. In this simple demo, it was only a track layout, but usually there are also some tables with extra configuration data. We did simulation, first interactive simulation where you can click and see what happens, and then scripted simulation where you can run test cases. It's very important to have good simulation support in order to discover unfortunate choices early. So even if your generic application has a perfect logic, you can make unfortunate choices in your configuration, like putting signals in bad places or stuff like this, and you will find it using test cases that this route can, for example, never be, you can never clear the signal because there are some not protection enough or whatever. Therefore, be sure to have simulation already at the desktop with the engineer. So the old-fashioned way of having a dedicated simulator room in the basement and do all the design first and then give it to testers, that's not a modern and agile way of working. You should, of course, have independent testers in the end, but it's also very important that the developers can test what they are doing all the way. So we discover things early. And the same holds with formal verification. Formal verification is a way of proving correctness with 100% coverage, so using mathematical logic. And it's famous for taking a very long time if it's done in the wrong way. But if it's done in the good way, it can actually be very quick. Like here, it was a small station, but yet it was proven to be correct within fractions of a second. And for bigger station, it can be maybe a couple of minutes if it's a really big station, but you shouldn't have to wait weeks. Okay, and then code generation, nothing really, no work really spent here, just press the button. All the work has been done earlier in the design phase, and simulation and investigation and so on. Okay, now certification. The idea we have for certification, the one that has been used in Senelec SIL4 projects and approved in such project is the following one. You use two sources for code. So, for example, you can use the source code and the compiled binary code, or as what we will do here, we will take the generated C code, and then we will, or it could in other projects be imported source code, but here is generated C code. The other channel could be compiled binary code, or as we will use it in this project, it will be a logical code model. So we will dump from ProverILOC a code model that's not C, but a logical code model, and we will prove using Prover Certifier that these two are equivalent. So proving equivalence of those two only prove that the generation of the C code has been correct. It doesn't prove that the C code is actually safe. It proves only that the C code agrees with the model. The next step, the safety requirements, you need to enter in the generic application. You need to put them in the generic application saying that these safety requirements are the ones that are supposed to be proven correct using formal verification. You need to review them to be sure that they are correct. You don't have to review the generated code, but you do have to review your safety requirements. The good news is you only review them at the generic application level, so you don't have to review them every time you make a new specific application, only when you change your generic application. And except for these generic safety requirements, you also need to enter some configuration data, and those are reviewed at the specific application level. You need to do that because you need to check that the configuration data you put into the process agrees with the actual configuration out there. All this data is put into Prover Certifier, and out you get a proof. So let me show you this. We already generated code. We also need to take the model from ProverILOC, and we need to take the safety requirements. So we can actually dump those. Here, you can dump the model, generate HLL code model. So here is now a mathematical representation of the system to be proven equivalent with the C code. Then we generate also the certification data. So I said it's generic, but that's only the safety requirements. The other stuff, all the configuration and so on, is specific. So here is all the stuff generated here. Let me see. This is the generic stuff. The rest is for this specific application. Okay, now to run Prover Certifier, it's not a Windows application. It's actually a Linux application. So to make it a bit easier for everyone who uses Windows at their desktop, we have a cloud-based service, which I will use for this demonstration. So we need to send the generated C code, the certification files, and the HLL code. So first, I need to zip those by creating an archive, zip folder like this. And then I need to send them. So let me copy the path here, and I go to a site, cloud.prover.com. And here we have different tools, but now we use the Prover Certifier for Trident Demonstrator. We need now to choose the file. Take this, the zipped one I created, and then we run certification. So you can see here some old ones completed, and then there is one that's scheduled. So it means that when the server is available, it will start this job, it will do it, and it will email me. I have an account here, so I will get an email when the run is done. So while we are waiting for the run, let's sum up what we did here. We collected all the relevant files in a zip archive. We ran Prover Certifier on Prover Cloud Apps. It is also possible to transfer the relevant files to Linux computer and run there. So if you don't want to send files over the internet, maybe you have some cybersecurity concerns about that, you can use your own server and run proof on this server. What remains now is to review the safety requirements and configuration data. As I said before, the safety requirements are reviewed once for the generic application, while the configuration data has to be reviewed for each specific application. It's a bit annoying maybe to have to use a Linux computer for this last step, to have to switch between Windows and Linux. But recall that the main work here will be done in Windows. You configure everything, you work with this, you discuss with colleagues, you send examples using PureILOC as a way to simulate what happens and so on. And in the end, you just use a web browser or a Linux server to do sign-off verification, meaning you're not supposed to find any bugs there. You just validate or verify that every safety requirement is fulfilled. Okay, I will go into the generic application process, but before I do that, let me just check if this run has started. It's running now, but it hasn't finished. This typically takes a minute or so before it starts, and then it takes maybe a minute to run. When we run this certification flow, we don't only prove that the safety requirements are fulfilled, we also prove the equivalence of two files. We generate and save a proof of the equivalence as well as of all the safety requirements. And when this file has been saved, the proof log, we run an independent proof checker that actually checks that the proof log is correct, so that we know that the model checker didn't make any mistake in this. So it takes a bit more time than the 0.4 seconds it took in PureILOC before. But let me get back to this and go on with the demonstration here. So the generic application process. I need to stop PureILOC because I'm about to change, to bring up and change some of the specifications here. I use for this Cygwin, which is a Linux-like environment in Windows, but you can use any way of handling files you like. Okay, I have my packages here, demo design 4.0. So let me show you something. If I open the implementation of the switch logic, and I like Emacs, you can use any tool for editing files, but here I will use Emacs. If we look at, and this is part of the answer also to the question I got previously, what is the package? Well, with a package, you have a number of files that define signaling principles. So here for this demo principles about the switch is a condition for when to throw the switch to the left and when to throw it to the right. You can see here that there are 5 conditions that need to be fulfilled for throwing a switch to the left. The first one is that it's not locked. This is a not sign. The switch must not be locked, and the switch must not already be placed to the left. Then there's no point of throwing it to the left. The switch must not have a write request, so a request to be thrown to the right by the human machine interface of the Office system. And it must not have a request to be thrown to the right by some route. So when you request a route, the switch moves, as I showed before, and there must not be anyone that wants to switch to the right. And so these are 4 negative conditions, and then there's a final positive condition that either you get a request to throw it to the left from the Office system, or a route needs it to the left. So pretend now that we have a little error here. We introduce a typical error. So instead of saying left, we say right. You're a bit confused when you write this, so you put in there right instead of left. Let me now open this little project I have. I need to open it like this. Here we have it. If I open it up now, it will load again all these packages. As I said, it takes a bit of time because it checks first that there are no changes in any of the packages, and there are quite some packages with quite a lot of files in them. So this little check takes some time. And actually, it will probably show us a little change now because I changed this file. Yes, it says integrity checked failed. There is a new automatically saved file in here, but there is also modification in this one. Okay, so but I ignore that now because it's for demonstration purposes, and let me start this one. So for example, this one, this is a switch here. The logic for throwing it to the left has been changed, so it will not work anymore if I request a route like this. It will not throw the switch. But I didn't change the possibility to throw the switch by a manual request from the human machine interface. So we can try this one. And also see what this, how we can discover such errors using simulation and formal verification. Okay, let's open up the simulator. Here now, if I request this route, you see that the switch here doesn't throw anymore, and the route remains requested, it doesn't lock. But if I send this left request HMI, the switch will throw and the route will lock. For routes with I only changed the condition for throwing left, so no routes to the right will be affected by this. Let me take away this route, releasing it. If I run scripted tests, you will also see here that some tests are now red. If you look at some tests, you see that most of them work, but 2 of them don't. And it's because 2 of these routes have required switches to be thrown to the left. This one and the other one is the exit route here. So you see S1 to S4 is from signal 1 to signal 4 here. And the other one is S3 to exit, so from here and out. So here is a very convenient way of discovering strange errors in the generic application as well as in the configuration data. If we run formal verification, however, this will not, everything will still pass. It's all green because the error we introduced here was not really safety critical. It just prevents some routes from being locked. So you don't get any safety hazards with this. So I want to show you also some other example where you actually introduce something unsafe. Let me revert this left, and then let's look at the locking conditions up here instead. For locking, this is an OR symbol. So for locking, we say that there are 4 different reasons to lock. The first here says that the switch's track, this track circuit on the switch's track is not vacant. That's a reason to lock. So if you occupy a switch, you are not allowed to throw it. The second one says that if there is a track circuit path, so a path of the track circuit that locks the switch, then the switch should be locked. And then there's flank protection reasons and front protection reasons to lock the switch. I'm not going into details because this webinar is not really about the signaling principles, it's about the tools and processes. So just imagine that we forget in the design one of these things. We forget the occupancy here. And I open up again this project. So // means a comment. So in effect, I remove this line. I comment it out. So I'm opening up again and validating all the files. Okay, here it says the same. This file is still changed compared to the checksum. And now if we run simulation, I'm pretty sure that all the safe requirements, all the test cases will pass now. Everything will be green. So we'll not find this error using tests, because there is simply no test for this particular case. But we will see that we can show it using formal verification. Meantime, I will go back and look at this job now. The job has finished, and we can see the run here. PSL has proven everything, all the requirements, and the log is here, and you can see in the end that everything was okay. Some requirements has been proved, and everything is okay. You also get an email with this, and you can download the log and everything. Okay, let's go back here. You can see all the tests have passed. But if you run formal verification, I'm pretty sure we will prove that some requirements are not fulfilled. Yes, we look here. Both switches, they violate this requirement. A non-vacant switch must not alter its position. So if you want to look more at this, you can double-click this failing, and it will create a scenario for you when the switch actually alters its position, although it's not vacant. So you can see here, it's ladder logic, and this means that vacancy is not on, so it's not vacant. And you can see that -1 means previous step, so it says that if it was sorry, I need to think of it here. It's about throwing to the right. It says that now it's put to the right, but it was previously not put to the right, so something has changed here, although this was not vacant. And if you click here and see why, you can see here that it checks this throw right and locked, and here you can see that there is no check anymore for vacancy. So actually here you can view all the equations in the design using ladder logic, which many signaling engineers find very convenient. You can see with the blue here means that the metaphor is that it's like a closed part of the circuit. Red square means that it's a broken part of the circuit, an open part, and moreover it might be the explanation to why this why the whole circuit is not closed. Okay, actually that was very briefly, but yet a walkthrough of also the generic application. So I changed some signaling principles and investigated the impact. With some simulation, we could show how a small change turned out to have big unwanted impact on how the interlocking functions. And formal verification showed problems in other cases. So notice that I gave you an example of one problem that can be found with simulation, but not formal verification, and another problem that can be found with formal verification, but not simulation. So they're not necessarily the same. It also depends on what safe requirements you have actually put into your bunch of requirements you want to have proved. You want to prove with formal verification. It's largely up to you. This webinar hasn't focused on the entire generic application process so much. The process itself is not very different from a usual generic application development process. We firmly believe that a good generic application development process is to use a very good specific application process. You can try all the time what you're doing. And this includes doing continuously some simulation and some formal verification so that design is changed early if it covers only 99% of the cases and not 100% as we want when we are doing serious software development. So if you want to work like this, you don't necessarily have to choose our prover trident to work like this. It's also a concept that you can implement yourself. Nevertheless, I would say it's very important that you integrate tools as much as possible. So if you, for example, only have automatic code generation and no simulation and no formal verification and so on, then you will have poor results because you can generate the code, but in the end, it will have bugs and you discover it late and so on, and you need to change your generation. So be sure to integrate the tools as much as possible. And then make V&V tools available to all involved engineers. So you shouldn't have a dedicated tester in the basement testing everything only. You should have tools available to all engineers so they can find themselves their bugs. They are usually, from finding a bug to fixing it, it's very short if it's the designer himself who finds the bug. So that's the recommended way of doing it if you want to save some costs. And then it's also important to bring your staff on board. So a bit funny perhaps, but common question is that we get is, what do we do with all this staff that are suddenly replaced by tools? Well, the railway engineering business is very large and growing, so I'm sure that you can find ways to interesting tasks to give to all these senior engineers you have. The senior ones can work with writing down the generic signaling principles in logic so they become precise, and you can deliver more projects with the same staff in the end. To start this generic application development, you need to write specific specifications for the line you want to signal. So maybe you have a project somewhere and they have their peculiar signaling principles and they want you to follow that. Then you need to write specifications for that. The first one, which is very important, is an object model. So the good thing with it is that it can have very high precision, although you don't know a lot of what you're doing, which is typically the case in the beginning of a project. So in an object model, you write down all the objects you need to support. Like there are switches, there are track circuits, there are maybe train routes, there are shunting routes, different types of objects like this. And then you write down what inputs and outputs these objects have, and also some important intermediate variables that you might have safety requirements on, such as route locking, which is not really an input or an output, but something important that your infrastructure manager wants you to prove properties about. Put all these things in an object model. You don't have to explain how they work, how they are implemented, but you need to explain the interface. So for example, this input here is from a switch, detecting that the switch is actually to the left. This output here is for throwing the switch to the left, things like this. Then design principles. You need some fundamental principles strictly specified, and the rest, all the details can be developed along the way in an agile way. You write down also some tests or use cases, simple scenarios written early that can guide you through development. You say simply that I want it to work like this. When I request the route, I wait for a few seconds, then the signal is cleared. Things like this. And the safety requirements, they are not scenarios. They are properties that you want to be always fulfilled, such as that a switch can never throw under a train, things like this. You can do this yourself, or you can let us write the specifications. We have services for doing that and have been doing it many times. Usually we depart from example programs, drawings, or whatever you have, write specifications, and then we work together with you on them. You need to allocate an expert that can answer all our questions during this work, of course. Then the third step is to formalize the specifications. So we need, again, an expert that can answer questions. Otherwise, we can do this for you, or there are many skilled consultants that can write specifications. And when I write formal here, I don't mean formal in the sense of legally binding, but actually formal in the mathematical sense. So it needs to be formulas. The first step, if you want to increase automation in your process, could be to have a meeting. We could set up a meeting with you if you want, 1 or 2 hours. We can use Skype or Microsoft Teams or similar, or we can meet face-to-face, depending on your needs. And during this meeting, we would review together with you the current process and the challenges you have. And in the end of the meeting, you would have a fairly good understanding and a plan for how to increase automation in your process. Okay, actually that was all I had to say. We have had a couple of questions. Lars, can you?
Hi, Jesper. Yeah, there is a couple of questions. We have a couple of questions, so we'll move over to Q&A. And before we start to answer the questions that's been sent to us, please check the GoToWebinar control panel for the question mark icon. You can type in your questions there if you haven't done so already. But here we have the first question. I think it's best if you read it out loud, Jesper.
How many signaling principles exist in Prover iLok, and how many signaling principles around the world? Okay, as I said, in Prover iLok proper, there are no signaling principles whatsoever, but they are in these packages. And we have a few that we own. Otherwise, usually our customers own their packages. So it depends a bit on what you want. If your signaling principles happen to be close to the ones we have supported before, then we could license this package and so on. Otherwise, we could build something together.
Good. Another question. I hope that was a good answer. Hi, what's programming language has been shown in the packages?
Yeah, what I showed was a language called PySpec that we invented at Prover some 15 years ago or so. It's a domain-specific language for configuration of signaling systems. So it's essentially, if you're familiar with logic, it's like first-order logic with a type system on top.
Yep. Another question, what interlocking platforms do you support?
Yeah, in the code generation, we can generate code for some general purpose languages like C, for example, as I showed in the demo. But we have also done it for Microlock, VHLC, Electrologics, IVPI, Westtrace, and a few others. All those I mentioned now are Rails-specific languages. But it's also done in a way that we can extend this. If we would have a customer that wanted to use a new platform, we could extend it easily by adding a new plugin.
Yep. Some more questions coming in. Is there a possibility to translate the... Right, it was not complete the question.
Oh, okay. Maybe there's a second question from the same guy.
Is there a possibility to translate
a specific project?
Yeah, there it is. We'll do our best to help out.
Okay, so we have, is there a way to translate a specific project to relay circuit? Yes, maybe you mean to import logic. This we have been doing. There are two ways to import logic. If it's if it's a relay-based system, usually the logic is in a drawing or in many drawings. And we have a separate project that I didn't show today that's called the Prover Extractor that can read relay schematics and translate it into logic. We also have had a number of projects where we import programs for example, ladder logic programs, Westtrace and similar, into Prover iLok. So you don't have to, if the question is this, I think it is, please confirm. But if this is the question, then yes, we can import logic rather than write it.
Yep, we have another one. Can you repeat the language you have shown? Yeah, you just talked about that, but can you repeat the language you have shown?
If I can say again, it was called PySpec. If it's, I can send some information after this webinar with a few links. I think it's more.
Yeah, and if you want that information, you can maybe send a specific email to Jesper. You will have a Jesper's email address in the email that will be sent out after the webinar.
Yeah, that's a good idea.
That's I think the easiest way to get the detailed answer for that one. Okay, we have another one. Okay, I have about 10 questions I can ask you, or we can take it offline. Yeah.
Please don't hesitate to email me. As Lars said, we will include my email in the email that will be my email address in the email that we will send out.
Yeah, you will receive the email. Maybe it might take a couple of hours, but we'll definitely receive the email with Jesper's contact details, you can set up a separate meeting if you have a lot of questions. So, okay, we have another question.
The product supposed to replace manual programming, or is it for test after design? You can do both. So if you do everything I showed today, it replaces manual programming in the sense, well, you still have to program, but you do it, you program the generic application instead of specific application. So this is maybe the sweet spot for us. There are many lines out there where people program a little controller for each station. So maybe 20 stations need to be programmed. Instead, you write down your signaling principles in a language that can express this on a general level, such as PySpec. And then you can just generate the programs. You don't have to do them manually anymore. Our experience is that break-even is about 4 or 5 interlockings. So if it's less, then it's more efficient to actually write each interlocking manually. But if it's more than 4 or 5, it's more efficient to write the generic application and generate the logic.
Okay, we're almost running out of time, but we have 1 or 2 more questions, so we'll see. That one.
Which requirement a platform has to fulfill to use your generated code? Well, it needs to have a clear specification, so the execution model is clear for us, because we don't only generate code, we also need to make a simulator model and a verifier model, so we can prove correctness about the programs, and we must be sure that the execution model we use is in agreement with the real execution. So documentation needs to be good. Then it's especially good for equation-based platforms, but that's only the sweet spot. It's possible to do also for other kind of platforms.
Okay. Do we have to write all our signaling principles in formal logic?
Yes, if you want to generate code or prove safety requirements, you need to write down what you want to prove and how the features are supposed to work in formal logic. But as I said, if you don't feel confident in doing this, we can help you, or there are many skilled consultants out there that could help you with this.
Okay, yeah, it's now almost 4 o'clock Central European time, and we have to close down this webinar. But I think we actually managed to answer all the questions. Anyway, so
the 10 ones.
Yeah, exactly, the 10 ones. So maybe a separate meeting for that. But anyway, we will send out email later on with the presentation and also with contact details, so you can get sort of further help. So thank you everyone for taking your time to attend this webinar, and yeah, thank you, Jesper.
Yeah,
thank you. It's time for us to close down the webinar.
Bye-bye.
Bye-bye, everyone. Thank you. Bye-bye.